first question of revision 5 is identify the poles of the magnet. Here is a magnet in which we have to identify these poles. Here we can see the magnetic field lines are emerging out from this corner, and here they are merging inside the magnet. So this will be a north pole and this will be the south pole, as we can see here. I have shown it here because from a magnet, from the north pole the magnetic field lines emerge, and on the south pole the magnetic field lines merge. Now the second question is state Fleming's left hand rule. According to Fleming's left hand rule, if we hold our left hand in such a way that the forefinger, thumb and the middle finger are in a mutually perpendicular to each other, and if the forefinger is showing the direction of magnetic field, the middle finger is showing the direction of current, then the thumb will show the direction of force acting on the conductor. Next, the third question is name the rule for finding the direction of magnetic field produced by a straight current carrying conductor. The rule for finding the direction of magnetic field produced by a straight current carrying conductor is Maxwell's right hand thumb rule. Now, according to this rule, if we hold a straight current carrying conductor in our left hand in such a way that our fingers are encircling the straight current carrying conductor in such a way that the thumb will show the direction of current in the conductor, then the direction in which our fingers are encircling the conductor will show the direction of magnetic field around the conductor. Actually, the field pattern produced by the current in this current conductor is in the form of concentric circles. The center of these concentric circles lie on the conductor. What is a solenoid? Now, a solenoid is a long coil containing a large number of closed turns of insulated copper wire. Now, list 3 ways in which the magnetic field strength of a current carrying solenoid can be increased. Actually, there are 3 ways by which we can increase the strength of magnetic field produced by a solenoid: by increasing the number of turns in the solenoid, and by increasing the strength of current in the solenoid, and the third is the nature of core material in the solenoid. That means it should be a soft iron core which will enhance the strength of the magnetic field produced by the solenoid. Now another question is differentiate between an electromagnet and a permanent magnet. A bar magnet is a permanent magnet and an electromagnet is a temporary magnet, because its magnetism is for only the duration of current passing through it. So the magnetism of an electromagnet can be switched on or switched off as desired or required. Now, a permanent magnet produces a comparatively weak force of attraction, and on the contrary, an electromagnet can produce very strong magnetic field or force. The strength of a permanent magnet cannot be changed, and in case of an electromagnet, the strength of an electromagnet can be changed by changing the number of turns in its coil, or by changing the current passing through it. And the north-south poles or the polarity of a permanent magnet cannot be changed, and on the contrary of this, the polarity of an electromagnet can be changed by changing the direction of current in its coil. Now the next question is an alpha particle, that means positively charged particle, enters a magnetic field at right angles to it as shown in the figure here. Explain with the help of relevant rule the direction of force acting on the alpha particle. Actually, we have to use it here, Fleming's left hand rule. The direction of alpha particle will show the direction of current here, and this is the magnetic field, direction of magnetic field. So by using the Fleming's left hand rule, as we can see here, this is the direction of current, that is the direction of alpha particle, and this is the direction of magnetic field, as we can see in the figure. So the direction of force acting on the alpha particle will be in the outward direction of the page. The next question is, a coil of insulated copper wire is connected to a galvanometer. What will happen if a bar magnet is pushed into the coil? Now, as the bar magnet is pushed into the coil, there will be a change in the magnetic field around the coil, and because of this change in the magnetic field around the coil, there will be an induced current, and because of that, the galvanometer will show deflection in one direction. Now, the second part of this question, if the bar magnet is held stationary inside the coil, then there will be no deflection in the galvanometer, because if the bar magnet is stationary, there will be no change in the magnetic field around the coil, and there will be no induced current in the coil, and because of that, there is no deflection in the galvanometer. The next question is, state the rule to find the direction of force acting on the electron. Here is the figure. Here we must have to remember the direction of current will be opposite to the direction of electron. So if we are taking this figure, if we are holding our left hand like this will be the direction of current, this will be the direction of magnetic field, then the direction of force acting on the electron will be into the page. What will be the direction of force acting on the electron? So it will be into the page.